No? There we go. All right, guys. So, like I was saying, next week is your final, and it is cumulative, and it's going to cover everything from Unit 1 all the way up to Unit 3. And I'm thinking maybe possibly the topic we'll talk about today, but I'm not sure. It should be easy points, I think. I think I should throw it on there just because I think today's topic will be a little bit easier. Well, I'll ask you guys about it after we finish the lecture on it. What I wanted to talk about before we get into the lecture for today is your semester 1 final project. That one is also due next week on Thursday, and I think it's fairly simple. Here's what I want you to do. I want you to go through everything we've learned this semester and create a nice outline for it. Now, when I say create this outline, I'm going to let you decide however you want to do that outline. If you want to do it on Google Docs and just bullet point everything, right? I'll give you points for that. If you want to go through and be a little bit more in depth, I'll give you more points for that. And if you go in there and show examples or have explanations of how to do certain problems, I'll give you even more points on that. And the thing I wanted you to understand from this is that there's no cap. I'm doing this in my other classes as well. There is no cap as to how many points you can earn. Okay, there's no cap to how many points you can earn. So if you earn over the set points, I think I'm going to set this to about 50 points. If you earn more than 50 points, it counts as extra credit towards your grade. And I think that's I think that's fair, right? I think that's fair. It's a good way to help get your grades up if your grades are not at a place that you're happy with, right? And if you don't want to do that, you can still do the bare minimum and just get to what you want your grade to be at, or what grade you want for your final grade to be at. So if you already have an A and you don't want to feel like doing that extra work, you don't have to. But if you have like a B or a C and you want to work your way up to an A, this is your opportunity to do so. All right, so I'm looking for things like for you to, for sure, outline, right? Outline each unit, right? Meaning from Unit 1, Unit 2, and Unit 3, right? Unit 4, you're only going to have one section on there, so there's not going to be much form on there. But if you want to throw that on there, I will give you points for that if you do that as well. So if you're having trouble figuring out what we did in those units, remember all of these units and notes have been posted online. If you go ahead and head over to my Canvas page, if you look at the notes right here under period 3, you actually can gain access to everything that we've written from Unit 1, right? All the sections. What the heck happened here? Oh, that's the review. Yeah, Unit 1, all the topics that we covered from Unit 1 all the way up to Unit 3. And then if that's not enough for you to get your information from, you can also go onto College Board on my AP, collegeboard.com. There are Unit 1 and Unit 2 and Unit 3 actually sync up pretty well with theirs, right? So limit definitions of derivatives, right? Or using limits, actually, right? Was all of Chapter 1 and evaluating limits and all that, right? You can look at their videos to see and help figure out what exactly was covered in those topics. And if you can click on the units themselves, they'll actually tell you what was covered in there, but it's not very much just by looking at the topic numbers. You can watch the videos, though, and see what was explained in those ones, and you could use that to help you, to guide you through that. Like I said, though, for this project, right, I'm not giving you any particular guidelines to it. I'm telling you that you can do whatever it is you want to do on there, and I'm going to grade you based on your effort and what information is on there, right? Second thing is how you organize it, right? I leave that, again, that choice is up to you, but the easier it is for me to read through it, the easier it is going to be for me to give you points for it. So keep that in mind. When you are creating this final project, you can do it anywhere you want. You can do it on Google Docs. You can do it on Google Slides. You're going to just submit that whole thing for me and make it easy for me to navigate through how you organize this pretty much like review of everything that we've done. Okay? All right. Do you have any questions so far about this project? Have any questions about what I'm asking from you? I'm thinking it's pretty straightforward, and I'm hoping that you guys are okay with that. Doesn't sound like it's too overbearing. I hope it doesn't sound like it's too much. I'm telling you right now, so hopefully you guys can have some time to work on it over the weekend. And I think for you guys to just work on this project. So after today, after we do our Unit 4 notes, I think that's going to be the last part of lecture. And I want to just give you guys time to work on that so you can have as much points as possible to turn in before the end of the year. Can we do it on a paper or just on docs? I mean, if you're going to do it on paper, make sure it's somewhat easy for me to follow. Does that make sense? Like, if you're going to do it in your notebook, that's perfectly fine, but take pictures of it and then organize it for me on Google Docs or on Google Slides so that it's easy for me to follow. If you have if you just upload 10 pictures for me and I have to go through there, it's just going to be hard to read. So make sure it's organized in a nice way. And if you want to do it on paper, you can, right? You want to, you know what would be nice? You know what I would appreciate is if, for example, you were doing this, right? And on your slide, the first slide that you have was like for, let's say, unit 1, right? And you, on one slide, you take a picture of yourself giving me a definition of something, right? Definition of something, and then you go on to the next slide, and what I want from the next slide is you showing me an example of that problem. And you could, if you did it by hand, you could just give me a picture of that and have that on the next slide, right? So make sure it's easy to follow through, and you can title the slides too, I believe, on Google Slides. That way I can see what it is, and you could put in the notes what you want me to be looking for in each of those slides. Okay? So that was a good question from you. Anyone from Brian? Anyone else got a question about what I'm expecting from this? To be honest, I'm expecting a lot because I'm trying to not bound you guys. I kind of want you guys to wow me with this. I know it sounds hard to wow me with calculus, but trust me, you guys are creative. You guys can do this. Wow. I believe in you. I believe in you. All right. Now, enough of that. So that being said, right, if you have questions, you can also ask me next week on Monday and Tuesday as well when I give you guys time in class to work on it. And that's going to be pretty much it from that. Okay, if you got pictures of things, that's even better. If you know how to use Desmos and you can graph a function and you can show me how it works, that's also pretty cool. Let me show you right now. Like, one thing that I would be like super impressed with, right, is if you could show me on Desmos or on a graphing app, if you when you get to chapter 2 and we start talking about derivatives, right, it would be cool if you could show me graphically what does a derivative look like, right? Do I have a function like that programmed? Yeah, like here, for example, like the definition of the limit, right, for a derivative, right? If you this one, yeah, there we go. Okay, so let me take off that guy for now. So for something like this, for example, if you give me a screenshot where you show me like, hey, if the original function is this parabola right here, the derivative at this point is supposed to be, oh, that was the graph of the derivative. Anyways, show me that the derivative value is the slope of that green line, right? And then you can graph the actual derivative itself. Oh, that's neat to look at. So when the derivative right here is 0, the graph of the derivative is the other line that's going across there. Is that this guy? Whoops. Yeah, there it is. Yeah. So stuff like that. If you show me screenshots, have pictures of it, have yourself have notes explaining from it, it would be nice. So you want like a chart of each unit and what we learned from it. That would be a nice way of looking at it, Juliet. If you want to do it that way, that's perfectly fine. If you want, give you points for that. I'll give you more points if you have in each of the charts, aside from what we learned, how to do an example problem. If you want to show me that, that would be good. If you want to record a video of yourself, or not a video, but like a sound clip of yourself explaining how to do a problem, I would give you more points for that. Again, like I said, I'm looking for you to just figure out, what do you think is going to impress me, right? Do you feel like I'm just going to be impressed if you only list out things in bullet points? Then yeah, you can turn it into bullet points, and I'll grade off to see how much you covered from each unit. All right, the more you list, the more points you can get. If you show me that within the bullet points you knew this is, how to do a certain problem. Again, there's no limit to what I'm going to give you for points wise. So if you want to go above and beyond and show me things like methods of how to solve these things or how to solve these problems, even if it's a method that we didn't learn in class, but you researched it and you found out like, hey, this works, you want to get this on there, I'll give you points for that as well. So that's the idea, right? The idea is I want you to be as thorough as possible, but if you don't want to go like too overboard because it's going to stress you out because it's going to take too much time from you, then don't do that much. You know, do what's comfortable for you, but at the same time, I want you to keep in mind like what you're trying to do is trying to like impress me, right? Trying to make it look somewhat, I don't know. I feel like, you know, I'm explaining this too much. I feel like you guys are AP kids. I think you guys are actually going to make the best project probably for this one. Anyways, that's that in a nutshell. Okay. And again, if you still aren't understanding it, let me know. Ask some questions. Come by my office hours today and ask me like what you think you want to do, and I'll tell you if that's okay, if that's enough, or if I want more from you, if I don't think that's going to be enough. All right. So that's that in a nutshell. But yeah, I'm excited. I'm kind of hoping to see some what I really want to see, and this I kind of like, don't want to give it away, but I really want to see like example problems aside from explaining like what the topic was. I would love it if you guys came up with your own example problems that I can't Google. You know, if I can Google your problem, I would be a little sad that you just took someone else's example. But if you came up with your own problem and you showed how to solve that problem, I would be like super impressed for each of the chapters. If you could come up with the example problem that isn't easily found online, and then you also explain how to do that problem, whether it be through like a voice recording of you or you typing it out as a paper, I would be super impressed with that. That's just an idea, you know, just an idea. Okay. Anyways, that's enough of me talking about this project. You guys get the idea, hopefully. And then, like I said, you'll have all time. I'm not giving out any more homework. You're going to have all, even though we'll probably finish 4.1 today, I'm not going to assign any homework from it because I want you guys to have time for this project. You'll have all of this weekend to do it, plus some in-time class on Monday, which is 30 minutes, which is not enough. But on Tuesday, you'll have all of third period Tuesday to do it. And then you'll be turning it in on Thursday next week. And then on Thursday next week, you'll be taking your final with me. And here's the kicker. The final, if you did your project correctly, you can, or not correctly. I'm thinking about this. I don't actually know. I'm thinking about letting you use your final project on your final exam because that just kind of makes sense to me. Does that make sense to you? Like the fact that you can work on this thing and it's pretty much a review for your whole thing, that you should be able to use it for your final exam. I feel like that's fair. If you put in the effort to do all that and you have examples of things and I ask questions from all of the whole entire year, you should be able to use your study guide on the final. I'm thinking that's what's going to be the case. All right. That's enough of that. Enough talking. Let's get in here. Let's talk about some actual math today on chapter 4, extreme values of functions, unit 4, right? Which matches up, by the way, with the College Board videos if you guys haven't seen that as well, right? And well, it's somewhere in here. Oh no, it doesn't actually. You're not here. Interpreting meaning of derivatives in the context. Yeah, I think that's about the right part. Yeah. Anyways, unit 3 matched up perfectly. It went all the way down to like calculating derivatives of higher orders, inverse trig functions, procedures, inverse functions, implicit, and the chain rule. I thought that was pretty cool. Oh, okay. Our unit 4 is going to be their unit 5. Yeah. Anyways, okay, let's get into it. So, extreme values of a function. All right, that's going to be the name of this chapter right here. So before we actually get into it, let me ask you guys real quick here, or not ask you guys. I want you guys to check this out real quick. Just take a look at this function right here. Let's say we have here y is equal to x squared, right? On the interval negative infinity to infinity, right? The domain of this function is from negative infinity to infinity. And if I were to graph this, right? If I were to graph this, oh my God, that is fat. Give me 1 second. Let's make that a little bit skinnier. Why are you? Oh, there we go. Sorry. So if I was graphing this, right, it would look something like It looks something like this, right? I could do a better job. Hold on. Perfect, right? Perfect. All right. So if we were looking at something like this, right? And I asked you guys the question. Let's zoom in a little bit more here. What is the minimum value for y? What would you guys say? What's the minimum value for y on this problem? 0, 0, right? That's because it's right here. The minimum value for y is 0. Now, when we look at that, though, I kind of want you to write this out, though, right? I want you to write it out as y is equal to 0, right? Y is equal to 0, right? Where is this happening at? This is happening at x equals to 0, okay? Looking at the same problem, what is the maximum? What is the maximum value for y? What do you guys think? What's the maximum value for y on this y is equal to x squared? Any ideas? Positive infinity. Yeah, this thing goes off forever, doesn't it? As x goes towards infinity, y goes towards infinity, right? So when we say that, that's going off towards infinity, or in other words, the maximum for this problem does not exist, right? When you say things like infinity and positive infinity, that's the same. It's just a more descriptive way of saying that not only does it not exist, right? Here's where it's heading towards, right? It's heading towards positive infinity, right? That's the idea, right? When you're looking at these extreme values, what's the maximum? What's the minimum for a value? Okay. I'll get that out of here. Okay. So what about this then? What if I change this a little bit? What if I instead say, hey, I'm looking at this function y is equal to x squared, right? But on the closed interval from -3 to 2. I'm looking at this function, same function, y is equal to x squared, but instead of looking at it from -infinity to infinity, I'm looking at it from only -3 to +2, right? I forgot to copy. I'm being lazy. Oop, there we go. So what if I'm looking at this guy? Hello? There we go. Okay, I don't know why my program likes to freeze like that, but let's just pretend that it didn't. So if I was looking at this, and I was looking at this on the closed interval, get out of here. I'm looking at this on the closed interval from -3 to 2 instead, right? That's going to be at about right here, all the way over to here, right? And everything in between. So I'm only looking at it from here to here. So I'm looking at this function at those values, right? And down here, of course, is still 0, 0. When I look at it this way now, what's the minimum now for my problem? What do you guys think? What's the minimum value for my problem here? Is it still the same as the minimum value that I found earlier? Is it still at 0? I hope you guys say yes, yes, it's still at 0, right? Yeah, Brian, that's right. It's still at 0. The minimum value for y is still 0, and it's still happening at x equals to 0, right? What about the maximum value for this problem, though? What's the maximum value of this occurring at? And I hope you guys can see it. The maximum is the highest value that this function can go to. And if I'm looking at it on this closed interval, it's no longer infinity, right? It's no longer infinity. It gets to a part that's higher than the rest over here, which happens to be at 2, 4, but that's not the maximum value of the entire function, right? The maximum value of the entire function is over here at this point at -3, 9, right? That's the highest it can go on this closed interval, okay? So when I ask you for the max for something, and we write it out, oh, the y value at this max would be equal to 9 when x is equal to -3. Now, when you're looking at things that are the maximum or the minimum, if you think about it, it's basically, for example, for the sake of maximum, right? When you're looking for the maximum, it's basically saying that it is the highest point compared to every point that's around it, right? Compared to every point that's around it. So this one was almost a max, right? It's not the max, it's not the, the global max, but it is definitely what we call a local max. It's max of value for the things that are around it, right? Every value that's very, very close to it is going to be lower than that 2, 4. This, of course, we consider a global max. The difference between the two is that the global max is the absolute maximum. It's the absolute maximum for the entire function, not only just the ones around it. And the same can be said for minimum. This is not only a local minimum, but it's also a absolute minimum. It's a global minimum. It's the slowest point that you have for this entire function, right? Now, let's take a look at this one more time. Let's say I was looking at the same function again, right? Y is equal to x squared, but this time we're looking at it on the open interval of -3 and the closed interval of 2. Okay, we're looking at it there. So same graph, right? Same thing. This time, right? We look at this guy. Same thing that's going to be asked. What's the minimum here? The minimum here is still going to be y is equal to 0 at x is equal to 0, right? It's still the lowest point. This point down here, 0, 0, that's still the lowest point, isn't it? And then, of course, like earlier, right, over here, we're going to say that that is going to be -3, and this is going to be +2. This is the point right here, 2, 4, and this is an open dot now at -3, 9. Now, what's the max on this problem? What is the max on this problem? What do you guys think? Is the maximum still happening at -3, 9? Is the maximum number there still at 9, at y equals 9? What do you guys think? What do you guys think? Yes or no? Is this still considered the max? No. No, it's not. Because it's not included, right? That's what this open dot means, by the way. When you have an open interval, right? It's not included in your domain, meaning we can't actually look at that point because we don't ever reach that point, right? And as Brian is saying, it's not exactly at 9, and you're right. But which point do we pick? And this is the trouble with open intervals. Now, Leslie's got the right idea. This one has a closed dot. We can include this one in completely, right? And this is going to be a relative max, right? It's locally a max because it's higher than every single point over here, right? There's nothing that's going to be higher than 2, 4 on this side of the graph. But it's not a global max. Not a global max. Why is it not a global max? Well, if I pick the point over here at -2.5, right? -2.5 will give me an output value, right? If I do -2.5 squared, what is that? What is -2.5 squared? Do you guys know? If I could turn on my calculator? I mean, there we go. All right, -2.5 squared, right? Comes out to be 6.25, which is bigger, isn't it? 6.25. And by definition, that is bigger than 4, right? And so 4 cannot be your absolute maximum. Absolute maximum needs to be bigger than every single point on your interval. So then, well, what if I pick a point over here at about 2.9, right? What if I pick a point at 2.9, -2.9, I should say? That one squared is going to be bigger than the 6.25, isn't it? Well, how close can I actually get to 3 without actually getting to 3? Do you guys know? What's the closest point I can get to that will make it so that will be the absolute maximum of it? Whoops. Well, yeah, knock me. 2.99 itself is just going to equal to 2.99. But 2.99 squared is 8.94, which is bigger than 8.41, right? If I do -2.999 and I square that one, is that going to be bigger? And it is. It's bigger by another decimal point, right? It's instead of 8.94, it's 8.994. So what is the absolute maximum for this problem here? And I guess the follow-up question, is there a absolute maximum for this problem? I hope you guys can see it. There isn't one. Every time I get a point closer and closer to -3, I can always get even closer without actually reaching -3, right? So in this particular case, the maximum here does not exist. It does not exist. When I have an open dot like this over here, I can't actually find a maximum because I'm going to keep getting closer and closer to it, and I don't ever actually quite get there. So you got to keep that in mind. That also affects the minimum as well. If you ever have an open interval and it happens to be the lowest point on your graph, you will not have an absolute minimum because you can never reach that point. You just get closer and closer, and the more you get closer and closer to it, the smaller it'll get. In this case, the closer and closer I get to this -3 on this side, the closer and closer I get to that maximum value, but I'm never going to reach it. I'm never going to reach it, and every single value I get closer and closer to is going to be greater than the value before it. Okay, so that's the idea. The maximum for some certain graphs, the maximum will not exist, and for certain graphs, the minimum will not exist, and you need to be able to find those guys. Okay, you need to be able to find those. Now, if you have, for example, a graph that looked a little bit different from that. Let's say I have a graph that looks like, oh, I don't know. Let's say I have an open interval graph that is open interval here. It goes up like this, and it goes down like this. Yeah, let's say like, yeah, why not? Let's say it goes down like this, down to here, and let's make that a little bit better. Hold up. It goes up like this, and then it goes down like this, and it comes back up right here. Right, and it's an open interval. Let's say that this, let's pretend that this is like -4 and this is +4. I'm looking at this random function right here, this random f of x. And I'm telling you that this function is defined on the interval of -4 to, on the open interval from -4 to 4, right? You're not going to have any minimum or maximum here or minimum or maximum here. But this graph itself does have a maximum. Do you see that? It does have a point that's higher than the endpoints. And it also has a minimum, doesn't it? It has a point that's lower than the endpoints. You see that? So not only do you have to look at endpoints to see if you're going to have a maximum or a minimum, but you also have things in the middle of your function that could define your max and min as well. And they happen right here. Do you notice anything special about those points? What's something that you notice about that? Right, the maximum's happening and the minimum happening. What do you notice about that? What do you guys see? Anything in particular? Anything that you notice? Anything at all? No right or wrong answer, by the way. I'm just asking. Do you notice anything? Nothing, guys? Nothing? Is it the derivative? Yeah, when in doubt in calculus, right? When in doubt in calculus, has to do something with derivatives. Is that 2 open circles? Yeah, sorry. These guys over here at the end, oh, I did not mean to erase everything. The endpoints are open circles, meaning that they are open intervals. Yeah, those are it. Now, the dots that are in the middle, though, those are not open dots. Those are just blue dots. And I'm saying that that's where the minimums can happen and the maximum can happen. It's when the slope is 0 or the derivative is 0 at that point. That's pretty much the definition, isn't it? If you look at tangent lines, right? If you look at just tangent lines, and you can picture me drawing any type of tangent line, like if I drew, like if my endpoints were like, let's say here, and it went up, down, up, down, up, and I was looking for particular potential maximums or minimums, Brian is saying that the slope is going to be equal to 0 at those points. And I want you to picture that. Can you imagine a tangent line that's working its way across this graph? All right, we have negative tangent lines here, tangent line here, positive tangent line here, positive tangent line here, tangent line there, tangent line here, tangent line here, tangent line here, and so on and so forth, right? At the points that we look at that might be the maximum and the minimum, right, those tangent lines have a slope that's equal to 0, don't they? Do you guys see that? They also have slopes that are equal to 0 that are potential maximums and minimums, right? You see that right here? This is potential max, this is a potential min, right? We call those points critical points. Critical points. A critical point is where and this is exactly what Brown was saying, is where the derivative of a function is equal to 0. Or it could also happen, right, if it's pointy, it could also happen when the derivative at that point does not exist. So when you're looking for maximums and minimums, right, you can check the endpoints if they're included. If they're not included, you still need to check them to see if they're higher or lower than these guys right here that we're going to call critical points, right? These critical points are the ones that have a possibility of being a max or have a possibility of being a minimum based off of that, okay? So that's the idea behind it. That's the idea of why we're going to be doing these next few problems. And it's basically to see if we could find a max or a min at these particular possible maximum minimums, which occur at these critical points. That's all a critical point is. Critical point is a possible maximum or a possible minimum on a graph. Okay, let's go ahead and do one. Let's say I was asked to find all critical points. All critical points. Oh, let's go with all critical values. Find all critical values. Okay. Let me zoom out a little bit. Let's make this a little bit thicker back to that. Okay. So let's say I was asked here to find the critical value for, let's say, for example, y is equal to x cubed minus 3x plus 4. All right, let's do that real quick. So writing this out, to find your critical value, right? The idea behind the critical value, remember, is just when the derivative is equal to 0. So if you're asked to find the critical values, find the derivative. So take the derivative of both sides here. I'm going to get y prime is equal to 3x squared minus 3. To find the critical values, all I need to do is take that derivative, 3x squared minus 3, and set it equal to 0. Solve for when this occurs, right? Solve for when this occurs. And when does this derivative equal to 0? We go ahead and add 3 to both sides. I get 3x squared is equal to 3. Divide both sides by 3. I end up with x squared is equal to 1. Take the square root of both sides. And whenever you take the square root of an x squared value, always remember that it's not just equal to 1, but it's equal to plus or minus 1. And those are your critical values. So when you're looking at your critical values, you have 2 right here. Oh, knock me. Your 2 critical values occur at x equals to -1 and x equals to 1. And you can kind of see it when you graph this guy. But I'll give you guys a second to copy that down while I graph this up for you. Let me take a look here. Cubed. That's 3x plus 4. All right. So if you guys take a look here real quick, I'll put this on a graph right here. If you can take a look, this is what the graph looks like, right? If I'm not looking for the max or the minimum right now. I'm just looking for critical points for possible max and minimums if I'm ever looking on a closed interval. And check this out. Right here at x equals to -1, right? If you guys can picture the tangent line has a slope that's positive over here. And then once it gets to -1, it flattens out and then starts to go negative. You see that? So a critical point, you could also say, right, aside from it being here, it could also be something where it's a possible chance for your derivative to change signs, right? It's a positive tangent line, a positive slope here, and then it becomes a negative slope. And then I look at +1, right? It has a negative slope as it approaches it, and then it reaches 0, and then it goes to positive on the other side. So those are my critical points. I have a critical point at -1, and I have a critical point at 1 right there. Okay? Those are my critical values for this. All right. Can you guys go ahead? Let's go ahead and try another one. Let's try another one. Let's take a look at this guy right here. Let's say I was asked to find, again, find all critical values. All right, find all critical values. So let's say I have, for example, right, y is equal to x to the 2/3 and I'm asked to find the critical points for this guy. Yeah. You guys remember how to do the derivative? Oh, can I scroll up real quick? Sure. If you guys are still copying it, let me go ahead and have that there so you can copy that and copy down this next example. Let me know, Max, when you're good, when you got it. You're good. All right. Let's take a look at this problem. So remember, when is a critical value there? A critical value occurs when either the derivative is equal to 0 or when the derivative does not exist, right? So let's take a look at the derivative of this guy. If I'm looking for the critical points, I need to find the derivative first. So y prime is going to be equal to, take the power rule here, this is going to be 2/3 x to the 2/3 minus 1, which is going to give me a negative 1/3. Okay. If you want to simplify it out, we could write this out as y prime is equal to 2/3 times 1/x to the 1/3, right? And x to the 1/3 is just the cube root of whatever's in there. So I have here y prime is equal to 2/3 times the cube root of x. There we go. To find your critical value, we just set this thing equal to 0. We just set this thing equal to 0. 2/3 times the cube root of x. When is that going to equal to 0? And that's never going to equal to 0, is it? 2/3 times the cube root of x is never going to equal to 0. There's no value I can plug in for x here that will ever get this to equal to 0. The only times fractions are equal to 0, by the way, is when the numerator is equal to 0. If I have a over b is equal to 0, the only way this can occur, right, is if a is equal to 0, right? That's the only way a fraction is equal to 0, is if the numerator equals to 0. And that's not going to be possible because 2 right here is a constant. There's no way that 2 will ever equal to 0. So does that mean that there's no critical values on this problem? Well, no, right? This function that we're working with, right, y prime, is a rational function, meaning it has your x in the denominator. And whenever you have a rational function, you also have function. You have to look at its domain where the function is not defined, right? So the derivative for this one does not exist. I hope you can see it. Y prime does not exist if you were to plug in 0 for x. Why is that the case? What happens when you plug in 0 for x? You'll get 2/3 times the cube root of 0, which is just going to be the same thing as 2/0, which is undefined. This is undefined, meaning the derivative is undefined. I'm sorry, it's not undefined. The derivative does not exist at x equals to 0. And that right there is considered a critical value. Does that make sense? It's considered a critical value. Now, why is that? Why is that? Well, if you take a look, right, you can actually see it on the graph. Let's take a look here. The function is going to be y is equal to, I believe, x to the 2/3. And what's going on there? What is it? What do we have here at x equals 0? Do you guys remember what that's called? It's a continuous function, right? It's not that the function itself doesn't exist there, but the derivative doesn't exist there. And we have a corner there. Not only that, cusp. Yeah, it's a pointy thing, right? So the derivative doesn't exist there, but the function does. And that function actually has a minimum value here, doesn't it? You can actually evaluate that thing at 0, but we can't calculate the derivative at that point, meaning the derivative does not exist at that point. And that's actually the definition of a critical point. And you can actually see it. That's considered a minimum on this graph. It's the lowest point on this graph. And it's something that we should consider looking into and testing when we look at these types of problems. So not only is a critical point when your derivative is equal to 0, but it's also considered a critical point if your derivative does not exist there, right? So you got to make sure you are keeping an eye out for that, right? Keeping an eye out for that. So that's how you find critical points in a nutshell. We'll practice finding more critical points along the way right here as we apply them to find our absolute maximum and our absolute minimum, okay? So let's go ahead. And do you guys have this down? Can I move on? I'm going to scroll down to the next example here. You guys think? You guys okay? I'll wait a second. I'll give you guys a second to copy it. Ava's saying yes. That's good. That's good. We can move on. As soon as we get a couple more people there, say yes. All right. Okay, we're good to go. No? Right when I scroll it, David. Wait, for those of you guys not know. Oh, I just saw the exclamation mark. Wow. Okay, so, oh, by the way, just in case, if you guys, if any of you guys are working with multiple monitors, right? Please note, I showed you this earlier. These notes are posted online and they are updated live. So if at any point I'm writing something too fast, you could always leave this open. If you have, you know, decent internet and a decent computer with multiple monitors, which I don't think everybody has, but if you do, right, you can open up this notes on another window, and you don't have to. It will be updated live, I believe, right? So if I click over here, if my computer will stop lagging, load, buddy, load. There it goes. So you can see everything that I'm writing live right here on the screen. So if at any point you ever need something, you can just scroll over here and you'll actually see it open. Boom. Hey, this is the stuff I'm writing right now. Look at that. All right. Anyways, let me get back over here. So let's go ahead and do a problem where I'm trying to apply this now to find out if I have a global, an absolute max or an absolute min. When you take the AP exam, they're going to call it something a little bit different. So finding global, this is one of the words they like to use, global extrema. Extrema sounds kind of nice, right? It kind of like rolls off the tongue a little bit. But extrema, right, this is just a fancy way of saying finding the absolute minimum or the absolute maximum. What's the absolute highest and what's the absolute lowest point on your graph? And here's the thing. If you're doing this on a closed interval, you're guaranteed a max and a min. Guaranteed. If your interval is closed from, like, let's say some value to some other value, and they use the brackets to close them, meaning they use the solid dots to close them, you're guaranteed a max and a min. If you're using an open interval, if one of them is open, you're not guaranteed both. Does that mean that they don't have it? No, it doesn't mean that they don't have it, but it's just not guaranteed. You might still have one maximum and one minimum, but you might not have both if it's open. And you'll see them as the more you approach them and what I'm saying here. But let's do one where they both exist, right? Let's take a look at one where they both exist. So if I have here, for example, y is equal to x squared minus 4x plus 3, and I'm looking at this on the closed interval of -2 to 5, right? And I'm trying to find the global extrema, or the absolute max and the absolute min. We just plug in some values and see what the outputs are and which one's your max and which one's what's the smallest and what's the lowest value and what's the maximum, what's the highest value that you have there. So which points do we test? You're always going to start off by testing the critical points, right? And how do you find the critical points? How do you find the critical points? All you got to do to find the critical points is take the derivative, right? Take the derivative. So y prime is going to equal to 2x minus 4. And the critical points occur when the derivative, 2x minus 4 in this case, is equal to 0. Well, when does 2x minus 4 equal to 0? We solve that algebraically, and we see that, oh, we're going to get 2x is equal to 4, and x is equal to 2. So that's one critical point, but that is not the answer to the question that's being asked, which is to find the global extrema. So how do you find the global extrema? All you have to do now is evaluate at the critical point in the original function. Evaluate. How do you evaluate? We're going to evaluate at x equals to 2. That's not a 2, knock me. That's clearly a 0. Right? At x equals to 2, and I just plug it in. So I have here y is equal to 2 squared minus 4 times 2 plus 3. I have here y is equal to 4 minus 8 plus 3. And I get y is equal to -1. So at x equals to 2, I have an output value of -1. I don't know yet if that is a maximum or minimum yet until I compare it to every other critical point and every endpoint. This is the only critical point I have, so I don't have to test anymore. So the other thing I need to evaluate this at now is I need to evaluate at the endpoints, right? At the endpoints. So my two endpoints are right here. I have one at -2 and I have one at +5. So I'm going to go ahead and test to see what do I get when x is equal to -2, right? And I plug that into my function, the original function, not the derivative. You plug it into the derivative, it's just going to give you the slope of the tangent line, and that doesn't really tell you too much at the endpoints, right? It just tells you is it increasing or is it decreasing, and we'll talk more about that next semester. All right, so I have here y is going to be equal to, let's try plugging in here, is going to be -2 squared minus 4 times -2 plus 3, right? And 3 looks funny right there. So I end up with y is equal to 4 plus 8 plus 3, and I end up with y equaling to 15. So at -2, I have an output value of 15. So that's not going to be our minimum for sure, right? Because 15 is greater than -1, so that's not going to be our minimum. It has a possibility of being our max, but we won't know until we test the last endpoint. So the last endpoint we're going to test is going to be x equaling to 5. X equaling to 5. So again, we just plug it in. We just see what we get. Y is equal to 5 squared minus 4 times 5 plus 3, right? Y is equal to 5 squared, which is 25, minus 20 plus 3. I end up with y equaling to 8. So the input value of 5, which is at the endpoint, gives me an output value of 8. So you just take a look now, which one has the highest value and which one has the lowest value, and that's your absolute max and that's your absolute min. So what I'm focusing on is what's the highest and what's the lowest here of the output values. This is what I'm focusing on right here to tell me if it's the max and the min. So which one is your max, which one is your min? Just looking at the numbers, -1 is the lowest value. That means that at x equals 2, we have our minimum, our absolute minimum, or our global extrema, which is that right there. Where is our maximum occurring at? It's occurring at x equals to -2, and I have an output value of 15. It's a high value there, which tells me then that this right here is our maximum value. And that's it. That's how you find your global extrema. You find your highest point and your lowest point, and you're done. What do you guys think? Easy or hard? This is an application of a derivative, basically, if you're looking at it. You're trying to see now, applying why we learn about finding derivatives, right? And all those techniques that we've done to find those things. But now we're applying it and trying to see when does that derivative equal to 0, so we can find these critical points that might show us where the maximums are. If I did not find that critical point, I might have thought this right here was the minimum because it's lower than the other one. But you know that's not going to be the case. You know your functions do all kinds of weird things in between your endpoints, and you need to figure out in those weird points that are going up and down all over the place, is there any of them that are the highest, and is there any of them that are the lowest, right? And if you graph that, you guys know that this right here, that right there is a, I believe it's, called a parabola, right? A U-shaped thing, and it's a positive parabola. So we have a low point in there somewhere. And since we're looking at it on a closed interval, that low point might be considered where the vertex is. Might be. If you guys remember the vertex formula, do you guys remember the vertex formula? X equals to -b over 2a. If you were actually to plug that in, you actually would get that same value that we have for our minimum right here, which is how this actually connects. That shows you that you can actually calculate that stuff. I don't know if you guys ever thought about this. You guys ever have you guys learned that formula, by the way? When you're dealing with a quadratic, the vertex formula, have you guys ever thought about this guy? X equals to -b over 2a. Have you guys ever seen this one? I don't know. When I first saw it, I was always like, where the heck do people come up with these equations? And why do they always work? And if you think about it, in a quadratic, right, it happens where the derivative is equal to 0. I don't know if you guys want to see that. You know what? I'm going to show it to you anyways. So in a quadratic, right, ax squared plus bx plus c in a quadratic, the maximum or the minimum is always going to occur where the vertex is, which is here or here, depending on which way it's faced, right? And in those cases, the derivative is always equal to 0. So if you actually look at this guy and you take the derivative of this and set it equal to 0, that's how they get that vertex formula. And you'll say, knock me, how do you take derivatives when you have a, b's, and c's? Remember, a, b, and c's are just numbers. So treat them as a constant. So if I take the derivative of this, I end up with 2ax plus b. That's the derivative of this guy with respect to x, right? And if I set this equal to 0, that's going to tell me where the local max or local min is, or the vertex is, because there's only one part of that curve. Set this guy up and solve it for x, subtract b over, you get 2ax is equal to negative b, and then divide both sides by 2a. This is where that freaking equation comes from. I don't know, I think it's trippy, but you can actually see it. They used calculus to find the vertex for this quadratic, and then they teach freshmen when they're learning. I'm not freshmen anymore. You guys don't learn this in IM1 anymore. You learn it in IM2. They teach sophomores this equation, or if you guys are, some of you guys are smarter. Maybe you were a freshman and you took IM2. They teach IM2 students this, and I just think it's kind of neat. I think it's kind of neat. They show them this equation on how to find the vertex, and you're actually doing it using a calculus skill to get it. Albeit, though, when you learn it in IM2, they don't tell you it's a calculus skill. They just say, here, memorize this formula. And you're like, okay, negative b over 2a. But you can actually see it. It comes from the idea of taking a derivative and setting it equal to 0. Setting it equal to 0. All right, guys. Here, try this problem. You ready? Try this problem out. Find the absolute minimum and maximum. Why did I put a question mark when I say find it? Find it? Find it. Right? For this problem right here, y is equal to x cubed minus 3, but I want you to do it on the interval, the closed interval, -3, to the open interval, 5. So go ahead and do that one for me real quick. I'll leave this up here for as an example so you guys can see what we did to find that stuff. But can you guys go ahead and attempt that real quick? There's no pair deck or anything for me to see this work because we only have like 15 minutes left, but I want you guys to try it and see what do you guys get for your absolute minimum and absolute maximum for this problem. So I'm gonna go ahead and give you guys, that took me about 2 to 3 minutes. So I'm gonna set you guys up for about, let's go 4.5 minutes. 4.5 minutes. Then you guys can see where you're at while you guys are working that. You guys been watching any shows or anything? I mean, I shouldn't be distracting you. You guys should be working, but I don't know. Seen any shows or anything interesting that's worth watching? Attack on Titan. I watched that this morning actually. I should have waited because it's like one new episode per week or something again, right? It's like, man, I can't binge watch it. Yeah. SNK. What's SNK? I'm gonna watch Drake and Josh from the beginning. Your class recordings. Wow, David. Wait, why is Attack on Titan called SNK? Also, David, nice if you are watching my class recordings. Japanese name? Oh, okay. I don't, you know what? I vaguely remembered what happened in season 3 because when I was watching it this morning, I know it's a flashback sequence and spoilers. But I need to watch a recap of the older seasons because I kind of forgot what happened because it's been so long. It's been so long. Yeah, I'm behind on a lot of my anime except for that. I've caught up on Attack on Titans. I caught up on One Piece. Full Metal Alchemist. Eric, if you watch that, you should watch Brotherhood. Honestly, if you are watching Full Metal Alchemist, you should watch Brotherhood, because Brotherhood is the one that follows the manga. Oh, good. Yeah, I I'm old enough to remember Full Metal Alchemist, like the first one, and they were following the manga pretty well up until like episode 30, and then what happens is like the manga's still out there, so they have to do filler episodes, and they just went up on a completely tangent thing, and there's people who say like they like that tangent more than the original, and I'm like, that's whatever floats your boat. But yeah, I was more into Brotherhood. I thought they did a good job with that. Mob Cycle, I saw I think I saw like banners for that, or at least like the videos to click on for that, but I haven't checked that out. Dr. Stone? No, I have not heard of that one. I don't even think I've seen the any images or anything for that one. I still need to catch up on My Hero Academia. Is that what it is? Yeah, I think I'm on the last season for that one, but I don't know. It got weird. I think the episode, the arc I was watching was when they were about to do like a school festival, I think, and I was like, I don't know how I feel about this. Yeah, so I'm a little bit behind on that. But yeah, that's my anime watching side. What was it? Last night I watched the movie on Netflix. I don't know if you guys have seen. It had like a heartfelt like family movie, or not a family. It wasn't a family movie, but it was like a movie about like a father and a son. The name of the movie was called Chef, and it was on Netflix. I think it's a Netflix only type of movie, but it was pretty good. I don't know if you guys get a chance to watch it. I suggest you watch it. It's pretty cute. But yeah, I don't know. I should stop watching stuff. I still got to grade you guys' things. I was just feeling lazy last night. I didn't grade your test last night. I should have graded it last night, but I was like, I'm just gonna relax for a day. I'll grade the stuff over the weekend. Grading can wait. It'll be done over the weekend for sure. I just needed a day off. All right. Let's see here. Where are we at? 10:24. Anime grind shall never stop. Honestly, though. Honestly. All right. Let's take a look here. All right. Let's take a look here. So I'm asking you to find the absolute max and min on this function on the half closed, half open, right? So grade the animes you watch. I mean, I'm not going to do that. I watch it for my enjoyment. All right. So when you're looking for this, right, the first thing you want to do is find your possible max and mins at your critical points. So you want to take the derivative of this guy, right? You want to start off by finding what the heck is the critical point. Right? What's the critical points? So that's going to happen when you take the derivative, which in this case is going to be 3x squared, right? And you set it equal to 0. So 3x squared equals to 0. When does this happen? This happens when x squared is equal to 0. Don't forget to do plus or minus, but plus or minus 0 is still just 0. So that's your critical point in a nutshell, right? That's your critical point. Now, is that your max or your min? I have no idea. You need to test it by evaluating, right, at x equals to 0. So you plug it in. Y is equal to 0 cubed minus 3. I end up with y is equal to negative 3. So I get the point here, 0, comma, that looks like a face, 0, comma, negative 3, which I don't know if that's a max. I don't know if that's a min. I need to compare it to all the other points. Right? So the other critical points there are no more critical points. So now I got to go ahead and move on to the endpoints. You got to test those endpoints. So this first endpoint I'm going to test is that x is equal to negative 3, and that is included into this graph. So it is a possible max or min if it comes up. So I have here y is equal to negative 3 cubed minus 3. So I end up with y is equal to negative 27 minus 3, which gives me y is equal to negative 30. So at x equals to negative 3, y is equal to negative 30. So clearly, this is not going to be a minimum, right? This is not going to be a minimum. That's impossible for this to be a minimum because this is lower than that. Okay? Let's test the other point. Next point we're going to be is the next endpoint is going to be at x is equal to 5. I have here y is equal to 5 cubed minus 3. You end up with y is equal to 125 minus 3, which tells me that y is equal to 122. So at x equals to 5, the output value was 122, which is clearly higher than that one. So this can also not be your max. But here's the kicker. This one is your minimum, right? This one is definitely lower and the lowest point you have on this interval. So this is definitely your minimum value. But do you guys understand that this is actually not going to be your max? This is not going to be your max, even though that's clearly the highest number that's there. Why is it not the max of this problem? Why is it at x equals to 5, it's not considered the maximum of your function? Because of the open dot, because it is not included. That is correct. That is the right idea. Since we have an open dot there, it's not included into your function, and it's not your maximum point. It never reaches 122. That's right. That is perfect. That is the ideal explanation I love hearing. So the graph for x cubed minus 3 is going to look something like this, by the way. And we have an open dot at -3. I'm sorry, a solid dot at -3. Right down here, right? And that's going to be at -3, -30. And then at 0, right? At 0, we had the point 0, -3, which is clearly neither max nor min. And then at 5, we have an open dot at 122, and it's never going to reach it. We'll get closer and closer, and we never get to define it. So for this particular problem, we say that the max on this one does not exist. There is no maximum for this problem, and that can occur. You can also have a problem that will not have a max or a min if both of the dots are open. Sometimes, we'll never know. It's just something that you have to look into and check. So it's never like a guaranteed, like there's guaranteed maximums or guaranteed minimums or guaranteed that they both don't exist. You just have to test out the points. And honestly, I think it's kind of fun to do because all you have to do is go in there and take the derivative and then set the derivative equal to 0 and just test the points along the way. Kind of fun to do. At least I think it's kind of fun to do. All right. Let's take a look at one more. Oh, wait. Do you guys need to copy that? Let me zoom out a little bit so you guys can copy that. I want to take a look at one last one here. All right. Let's call this one was example. Let's call it example 1. Let's take a look at example 2 here. For example 2, right, I'm going to have here y is equal to, let's go with this last one right here, x minus 2 to the 2/3 plus 4. And we're going to do this for the entire domain from -infinity all the way up to +infinity and see if we could find the global extremes. The global extremas. Oof. What's nice about me teaching in the classroom and not teaching back at home? I got a message right now. Girlfriend's telling me the dog has been barking nonstop all morning. And it's something I don't have to worry about because I'm not there. Well, I do miss her. If she was barking, I would call her into the office and then just have her take treats. But I'm not there, so I don't have to worry about it. All right. Ooh, excuse me. Oh yeah, I wanted to ask you guys, have any of you guys in any of your other classes, do you know, or could you tell me, do any of your other teachers use Edpuzzle? It's like the site where you watch a video and you have to answer questions along the way. You guys, a lot of yeses. Not for math. Well, yeah, I'm your math teacher, so I don't use it, but a lot of you guys are saying yes. How do you feel about it for your other classes? Not for me. Just how do you feel? Is is it like annoying or does it work pretty well? It's not too bad. Light work. Okay. Okay, I was just wondering. I was looking at it. I was like, it looks interesting, but I don't know. Especially for math, you can't actually turn in math stuff, I guess, because unless you're just doing numbers, it can sometimes be annoying. Okay. Easy, pretty cool. That puzzle is nice. I like it. All right. All right. I was gonna look into it, and then I was like, actually looking into it, and I was like, it's a little weird. A little weird. Anyways, I have about 5 minutes left. And this is what I want you guys to try to do here. You guys won't probably be able to, I don't think we'll be able to finish this, but let's go ahead and take a look here. If I take the derivative of this guy, y prime, I'm going to end up with a nice chain rule. Am I not? Nice chain rule here. Derivative of the inside is 1. Oh, that's lame. So that's an easy chain rule. Derivative of 1, I'm just going to leave that out of it. And do the power rule for the outside, which is going to be 2/3 times some stuff to the -1/3. Derivative of 4 is just 0. But what's the stuff that goes inside there? Thanks to our last test, we know that the stuff that goes inside there is just going to be x minus 2, right? So if you simplify this out and clean this up a little bit, you're able to see that the derivative here is going to be equal to 2/3 times the cube root of x minus 2. Remember, I told you guys you don't need to simplify it, really, but I'm simplifying it because we know that if I'm looking for the critical point, I'm looking to set this equal to 0, and I'm looking to solve it. Now, if it was up here, if you're comfortable with your skills on solving this one is equal to 0, then you're good to go. You're golden. I have trouble seeing it like that when I'm trying to solve it, so I rewrite it into a form that makes it easier for me to see. So I deal with the negative exponent, and I deal with the rational exponent, the 1/3, right? Rewriting it as the cube root instead. Okay? So when is this thing going to equal to 0? And I'm letting you know right now, this thing is never going to equal to 0, right? This thing is never going to equal to 0. It's impossible for equal to 0. But I do notice this, that y prime does not exist when x is equal to 2. Because what happens at x equals to 2? You'll get a 0 in the denominator, right? Which makes the whole thing just explode. So I have a critical point, don't I? I have a critical point at x equals to 2. Because critical points is not only when the derivative is equal to 0, but it's also when the derivative does not exist. And the derivative does not exist at x equals to 2. So let's go ahead and evaluate that and see what we get. X equals to 2 into the original function at the very top up there. I end up with y is equal to 2 minus 2 to the 2/3 plus 4. And I end up with y equaling to 4. So I end up with the point 2, 4. And I need to figure out, is that a maximum or is that a minimum for my function? And I'm just letting you guys know right now. Remember, what does this graph look like? Something to the 2/3. We graphed this earlier. It has a little cusp, right? It has a little cusp. And it actually happens to have a cusp where the minimum is. Where the minimum is. How do I know that's the minimum? Well, what you can do is test points around it. You can plug in points that are around 2. Like, for example, I could have evaluated it at x equals to 3 and evaluated it at x equals to 1, and I see what I get there. And if you were to do this, and I suggest you take the time and do it and plug it in and see what you get, you will get numbers that are bigger than 4. So that means that that point is the minimum. Now, how do I know it's the absolute minimum? There's no other critical points, and there's no endpoints. This function is actually increasing infinitely on both sides. So where is your maximum in this problem if this thing has no closed interval? Well, the max for this problem does not exist. And how do you know that? It's just something that you visually can see it if you graph it, or if you test a couple more points along the way and you see that the points keep increasing as you go further and further away. And it never changes from increasing to decreasing, because if it did, you'd have another critical point, right? If it ever goes up and then goes back down, you should have a critical point there. And mathematically speaking, you did not find any other critical points. So this thing is always going to be increasing if you were to test these points and you keep going out away from that critical point. All right, guys, that's going to be it. This is our first application of derivatives into what we do with our derivatives. And this is just one of the first and easier ones. And it's kind of boring, but it's kind of neat at the same time, right? Now you have proof that you can see, like, hey, I have a local minimum or a local maximum or a relative minimum, right? And I can prove that it's a maximum or minimum because the slope of the tangent line is equal to 0. In other words, the derivative is equal to 0. All right, guys, it is 10:37. I'm going to stop it there. Start working on your project, okay? You'll have next week to work on it. Come in on Monday with some questions as you're working on these projects. And that's it for me today, guys. Have a good weekend. Stay out of trouble, stay out of jail. Don't get pregnant. All right? See you guys later. So long.